So my name is Wulff. I'm working at CERN. I'm the CTO for AI on HPC at CERN openlab, which is a group part of the CERN IT department. And I'll be talking about how you can supercharge your AI workloads with hyperparameter optimization and high-performance computing. But I thought I'd start a little bit to give a little bit of background about CERN and the upcoming computing challenges that the high energy physics community and CERN is facing in the coming decades. Then I'll go into a introduction to distributed AI training and hyperparameter optimization. Then I'll talk a little bit about how you can actually run hyperparameter optimization workloads on HPC systems. And then I'll give an example from high energy physics called ML-based particle flow reconstruction, which is an application I've been working on for the last few years. So CERN is the world's largest laboratory for particle physics. It's located on the border between Switzerland and France, just outside of Geneva. So in the satellite picture, you can see the Geneva Lake over to the right, and you can see in white the Large Hadron Collider, which actually mostly lays in France, but also passes through Switzerland. And here, where it says CERN Meyrin, is the main site of CERN. This also lies half in France and half in Switzerland. Now, from space, you obviously wouldn't be able to see the accelerator because it's buried underground, so it wouldn't be visible from the surface. CERN's goal is to understand the most fundamental particles and the laws of the universe. So, not a small mission. The Large Hadron Collider is the flagship accelerator at CERN. It's 27 kilometers in circumference and buried around 100 meters underground. We have superconducting magnets which steer the particles through the ring. We have dipole magnets that bend the particle beams through the bends. And we have quadrupole, sextupole, and octupole magnets to focus the beam and stabilize it in the straight sections. In the accelerator, particles are accelerated close to the speed of light. We have two beams traveling at the same time, as you can see inside the beam pipe here. One beam is traveling in each direction. And a fun fact is that these particles travel about 10 kilometers per hour slower than photons would travel. And at 4 different locations around the ring, we have giant detectors which record new particles that are created in particle collisions. And we use these to answer fundamental scientific questions like, why is the universe made of matter and why is there hardly any antimatter? Why is gravity so weak compared to the other fundamental forces? And is there only one Higgs boson? And does it behave exactly as we predict through the standard model? Now, the LHC produces around 1 billion particle collisions per second. And this results in around a terabyte per minute of data stored in our data centers. But what actually happens in the detectors? Well, when the particles collide, the energy in the particles is converted into new particles. And then these new particles travel through the detector and leave traces in the different subdetectors. So what we measure is the energy, the direction, and the charge of these new particles that are formed. And a classic analogy that is often made here is that you can think of these giant detectors as 3D cameras taking around 40 million pictures a second. Out of these 40 million pictures, we actually only save around 1,000. We simply don't have enough storage to save all 40 million pictures per second. So we need to do some really aggressive filtering and select the 100 or the 1000 that are the most interesting. The LHC is due for an upgrade. The so-called high luminosity LHC will have higher luminosity. Basically, this means more collisions per second. This will start running in 2029. And actually, up until 2029, the LHC will have gathered only 10% of its total data. Already it has been running for quite some time. We still have 90% of the data left to be recorded. And this will run until around 2040. So on the plot up there to the right, you can see the solid line is the accumulated data gathered. And you can see at around 2029, when the HLHC will come online, we will start gathering data at a much faster pace. Now, higher luminosity also means more collisions per bunch crossing. And this basically means having more collisions happening simultaneously inside a detector. And this makes the collision event much more complex to analyze. So in the round 2 picture here, you can see that we have around 40 collisions per second. So this is how it will look now when we run the LHC. So each of these yellow dots is a collision point, and then we have tracks from new particles coming out from here. So you can already, with 40 collisions per second, it's not always super easy to tell which track belongs to which collision point. Now when we go to round 4, which is after the upgrade, we would have around 200 collisions per second. So this makes the data processing and the actual physics analysis of what actually happens in this picture much more complex. So we have an upgraded accelerator, which gives us higher luminosity and thereby more collisions per second. This gives us increased data rates. We also have upgraded detectors, which will have higher granularity. So basically this would be like upgrading your camera to have more megapixels. So this also increases the amount of data. We have changing filtering paradigms. As you remember, I said before, we only save around 1,000 images per second instead of 40 million. So these algorithms that design how this happens also change. So all this motivates lots of R&D investments into things like code modernization, HPC and hardware accelerators, and new techniques, everything from AI to quantum computing. Now in the plots here you can see estimated total CPU needs of the CMS experiment, the Atlas experiment, and then also disk needs, so storage from the Atlas experiment. Atlas and CMS are the two largest particle detectors at the LHC. And you can see here that there is a gap between the expected capabilities we will have and the expected need without R&D. So basically this is what motivates a lot of effort to try to reduce this gap. Now at CERN and at CERN openlab in particular, we leverage HPC resources in high energy physics, of course, but also beyond. So I just wanted to quickly mention a few of the different projects that openlab is a part of. Or was a part of. So we have first the COE RACE project, which is a project on research and on AI and simulation-based engineering. Then we have the InterTwin project, which was a project to co-design and implement a prototype of an interdisciplinary digital twin engine. Here we also developed tools to make it easier for scientists of different domains to use the power of machine learning. Andy also mentioned this in his talk this morning, the iTwin AI tool. We are currently part of the Spectrum project, which is a project that leverages the common vision and challenges between the high energy physics and the radio astronomy communities in order to develop strategic research agenda and a technical blueprint for how data-intensive sciences can use high-performance computing more easily and more effectively in the coming decades or so. We're also part of the Biodynamo project, which is a code for easily creating, running, and visualizing multidimensional agent-based simulations. This can run on HPC as well. And finally, we're also responding to a new Euro-HPC community COE, where we focus on codes from the 100 physics community in order to develop the codes to better and more efficiently use Euro-HPC JU systems. Now, before I go into the slightly more technical part of my talk, I just wanted to say that artificial intelligence really thrives at CERN. It's used in many different parts of the work that we do. Everything from accelerator systems, where it's used for things like beam dynamics and control, to the network and data infrastructure. It's used in the real-time data selection and filtering. So going from these 40 million pictures down to 1,000. It's also used in simulation with generative models for something called event generation and fast simulation. And it's of course also used in analysis, which is where we actually make sense of all the data that is collected. Part of this is the ML particle flow that I will talk a little bit more about in a few minutes. Okay, so let's talk a little bit about distributed training and hyperparameter optimization. I think probably all of you are not machine learning researchers, so I'll start very simply by telling you what actually training a machine learning model means. So basically in deep learning or machine learning, we have parameters that I would call W here, and these are learned using backpropagation and gradient descent in order to minimize some objective or loss function that I would call F here. So F depends on these learnable parameters W. It also depends on some other parameters, which I would call theta. So these are the hyperparameters. And when we're training our model, all we do is go through all the input samples in our training data, X. We run it through our model and get some output. We usually compare it to a ground truth of some kind with a loss function. We then compute the gradients with respect to the learnable parameters. And then we change these learnable parameters, or these weights, by going in the opposite direction of the gradient. And then we just repeat this for all the samples in our training data. We often repeat it many times for each sample in our training data until we reach some kind of stopping criterion, which may be that we run out of compute time, or that the model reaches some desired level of accuracy. So that's very briefly how training deep learning models work. Now, distributed training is simply training your model on anything more than one device, more than one GPU. This, of course, enables you to scale to larger models and larger data sets. And this is important not only because it allows us to have faster training times, but also faster development cycles. You can iterate through different versions of your algorithm much faster. We can also overcome memory constraints if we want to use larger models. And there are many different examples of distributed strategies. Data parallel is the simplest one. And then there are many different kinds of model parallel strategies. I won't go into all of them here, but I thought I'll just quickly talk about these three. So starting with data parallelism. Here we simply copy our model onto each device that we have available. So each GPU that we have has a separate copy of our model. So this means we can't actually scale to larger models, but we can scale to larger data sets. each device then is fed different batches of your training data, and the gradients are averaged and synchronized across the devices at each optimization step so that the models are kept in sync. So this introduces some communication overhead to your training. If you want to scale to larger models, you need to use some model parallel strategy. So one strategy is called tensor parallelism, and this basically splits the computation of individual tensor operations across multiple devices, so that each device just handles a fraction of the overall computation. Then we have pipeline parallelism. Then this simply means that we split our model into stages, and each sequential stage is run on a separate device. And we can sort of combat this sequential nature by overlapping the execution. So when the later stages run the first batch, then the earlier stages can already start working on the next batch. Okay. So with the distributed training comes some challenges. Of course, we get this communication overhead where we need to synchronize the gradients and weights between the GPUs. We can also run into data loading bottlenecks if your input pipeline is not efficient enough to feed all the GPUs that you're trying to saturate. We also get some increased debugging complexity, of course, when using more devices. And finally, there is this concept of a generalization gap, which occurs when we're training with very large batch sizes. This is also something that Andreas mentioned this morning, where we can see a degradation in model performance when training with very large batch sizes. And this is something that I recently encountered in my own work, so I want to spend just a couple more slides on this concept of the generalization gap. So I found this paper called Accurate Large Mini-Batch SGD Training ImageNet in 1 hour, which explained this concept quite well, I think. So these are two plots from the paper. The first one showing the generalization gap appearing when we're training with large batch sizes. So you can see the blue training is using larger batch size, and it never quite reaches the same level of performance as the smaller batch size training. We often combat this by just increasing the learning rate, but that's not always enough. So in this case, they also had to introduce a learning rate warm-up, meaning we start the learning rate off at a very small value at the beginning of the training and slowly increase it. This turned out to work in this case, but it doesn't always work. So in my own case, with MLPF, that we will see more details of shortly, we had the following situation. So we started with just a single GPU training, which is in blue here. Then I tried just using 4 GPUs without changing anything else. And to start with, it looked sort of okay. We have the orange line here. It starts to decrease slightly faster than the single GPU training, but eventually it stops improving, and it actually never reaches the same level of performance as the single GPU training. So then I did what you normally do. You scale the learning rate with the batch size, and then we got the red line. This again looked very promising in the beginning. It looks like we're learning much faster, but then suddenly we actually stopped learning, and this training actually even started to diverge. So here we needed to do some more hyperparameter optimization. We needed to tune the other parameters of our training algorithm. And in this case, it turned out that we had to increase the weight decay by a little bit, and then we got this final training where we were able to train much faster, and we actually reached an even better performance than the single GPU training. Now, what I want to say with all this is basically that speeding up your training is not as easy as just throwing more GPUs at the problem and then calling it a day. You might also have to change things in your actual training algorithm or your model. You might have to tune your hyperparameters. So that brings me to hyperparameter optimization. So you remember that the objective that we're trying to minimize depends not only on the learnable parameters, but also on the hyperparameters, the theta. So hyperparameter optimization, or HPO, is then simply the process of tuning these in order to improve the performance or to minimize the objective. So basically there are two different ways of minimizing the objective. We have training, which is the normal way, where we use gradient descent, and then we have HPO, where we're searching for some optimal hyperparameters. Now in the case of training, the reason why we can use gradient descent is of course because the loss function is differentiable with respect to the learnable parameters, but unfortunately it's not differentiable in general with respect to the hyperparameters. So HPO is a sort of black box optimization problem, which basically means there's no straightforward update rule for theta. So here we need to do something else. So basically we want to find this optimal set of hyperparameters theta star, but we only get to query the values of x, we can't compute the gradient. On top of this, f is also often very expensive to evaluate. We need to train a whole model to convergence before we know the value. Here we can see that we would have a great need of large amounts of GPUs that we know exists in our HPC centers, but we're also in need of smart and efficient search algorithms, so we use these resources as efficiently as we can. So here are some common HPO algorithms that you can use. So you can divide them in a few different ways, but the most basic way to divide these are into search algorithms and scheduling algorithms. So the search algorithms, they are the ones that decide which hyperparameters to try next in our search space, and then we have the scheduling algorithms, which decides when to launch new trials and when to terminate parallel performing trials early. So I'm going to go through a few of these now. Let's see. So starting with the most basic ones, grid search and random search. So grid search, of course, is deterministic. The user decides a grid in the search space, and then we evaluate all the points on this grid. The big problem with this is that we evaluate the same value of the same hyperparameter several times. So it's actually quite wasteful. So it's much better to use something like random search, where we randomly sample points in our search space and then it does an exhaustive search on these points. So as you can see in this nice picture, this explores the search space much more efficiently and means that we have a much higher probability of finding a good spot in our search space. Somewhat more advanced method is Bayesian optimization. Bayesian optimization is a black box optimization technique that is especially well suited for expensive or noisy objectives, which is exactly what we have when we're training deep learning models. In order to do Bayesian optimization, we need a surrogate model and an acquisition function. So the surrogate model is an estimate of your actual objective. It also gives an uncertainty for its own estimate, and it must be much faster to evaluate than to actually evaluate f, because otherwise we might just evaluate f. And then we have the acquisition function. So this is what selects the next hyperparameter to evaluate based on the estimate that the surrogate model gives. And this is where the so-called exploration-exploitation trade-off happens, which you always need to make in these kind of search problems. So here I try to illustrate how Bayesian optimization works. So we start with training a set of models, so running a set of hyperparameter values through our black box. Then we get a set of values for our objective function, and with those we can fit the surrogate model. Once we have the surrogate model, we can use our acquisition function to pick out the next set of hyperparameters to try. So this is this theta n+1 here. And then we run this through our black box and we get a new objective function value. So then we simply append this to our list of values, and we fit a new surrogate model. So we update this model with the new information. And then we can simply repeat this until again we reach some kind of stopping criterion. Now, if you want to run this at large scales in parallel, you might see that there's a problem here, because this is sort of very sequential. We need to always get the new value and fit the new model before we get the new value again, and so on. There is a trick, though, that you can use to get rid of this problem, and that is to modify the acquisition function. Modify the surrogate model to reduce the variance of this model to 0 at all the points which are being evaluated currently. And this stops the acquisition function from picking the same point again, which it otherwise would. And then you can just run these things in parallel. And then the surrogate model gets updated whenever we have a new value. Okay. So let's look a little bit at the scheduling algorithms. So these scheduling algorithms are sometimes referred to as adaptive configuration evaluation techniques. And this is because they change the way that we evaluate the trials. And this basically takes advantage of the fact that we can often identify badly performing trials early in the process. So why do we need to train them all the way to convergence? So for instance, in the plot here, we see a set of different learning curves, and you could probably tell already in the beginning part of the training that these higher ones would never really catch up with the lower ones already from the start. Now, so this is what these adaptive techniques are trying to take advantage of to terminate bad performing trials early. So some examples of these are the successive halving algorithm, Hyperparameter, and ASHA. Successive halving works like this. So we start to train some trials up to a certain decision point, which I've marked by these blue vertical bars in this plot. And at each decision point, we terminate some percentage of the worst performing trials. And then we repeat this through the whole training process until we reach the end of the training, or until there's only one trial remaining. And if we want to use the Hyperparameter algorithm instead, we simply repeat this whole process, but for different decision points. So basically by placing these vertical blue bars at different places along the training run. Now, you may be concerned that we are terminating good trials too early here. There's no real guarantee that a trial that seemed to perform badly at the start wouldn't actually overtake all the others in the end and win out. And that's just something that we have to live with here. Basically, the advantage of not spending all the compute resources training everything here to the very end is way higher than the risk of us missing some good performing trials. So basically, by saving all of these this compute, we can spend that instead on evaluating many more trials. So instead of starting maybe 100 trials to begin with, we maybe start 1,000 or even more. And this empirically gives us much better results than simply training everything to the end. Okay, so let's now look at how in practice we can run something like HPO on an HPC center. So for this we need some kind of workflow that manages everything that I just talked about. So you could do it like this, something like this. We have a driver which holds the search space defined by the user. It holds the search algorithm and the scheduling algorithm. And this driver is managing the whole process. It starts trials, and each trial then can set up the model and the hyperparameters that it was given. It runs the training. It can distribute itself onto one or more workers. And importantly, it reports validation metrics back to the driver. And these can be metrics like validation loss or model accuracy. And these inform then the search algorithm and the scheduling algorithm on what to do next. So mapping this onto an HPC system could look something like this. So normally we may connect to a login node using SSH. Then we might submit an HPO job through a job scheduler like Slurm. And we get access to a series of compute nodes with CPUs and GPUs. Then taking the workflow that we just had a look at, we could run it something like this. So we run the driver on the CPU. That's all it needs, and then it can launch trials on all the available GPUs that we have. And we can configure this in many different ways. We can, for instance, run one trial per GPU if that's all you need, or you can run one trial per 2 GPUs, or 3 or 4, and so on. Often, what I do is simply I run one trial per node, so using all the GPUs available in that node. So here, I also wanted to point out that there are basically 2 levels of parallelization going on. One that is connected to the hyperparameter optimization, where we run many trials of the model in parallel, and one where each trial in turn is parallelized onto many GPUs using distributed training. Okay. Now, I wanted to give you some results from a real-world example. So this is results that were partly obtained in collaboration with the CMS experiment at CERN, and part of it was also done as part of the C-Race project, and as a collaboration between CERN openlab and the Simons Foundation. So event reconstruction at LHC, just to give you some background on the problem that we're trying to solve. Here you can see a slice of the CMS detector at CERN. So the particles are happening at the very left of the picture here. That's the center of the detector. These particle detectors that we have are extremely complex, and they have many sub-detectors. And as particles travel through them, they interact with the different sub-detectors, and they leave tracks and energy deposits. And then what we do is we combine the information from all these different subdetectors and produce particle level interpretation of the event. So that's what event reconstruction is. The process of inferring higher level physics objects from detector signals. Another way to look at it is that event reconstruction tries to solve the inverse problem of particle to detector interactions, or in other words, going from the detector signals back to the particles that gave rise to them. And there is a long chain of algorithms doing this, going from the raw electrical signals from the detector to fully reconstructed events. Now, one of these algorithms is called the particle flow reconstruction algorithm. And that takes tracks and clusters, which then have already been reconstructed by some upstream algorithms. Takes these as input and then gives particle types and their momentum as output. So this particle flow algorithm is a non-machine learning based algorithm that has been around for a long time. It was developed in the CMS collaboration at CERN. And it tries to identify and reconstruct all the stable individual particles in a collision event. And it does that by combining information from different subdetectors. Then we have the machine learned version of this, machine learned particle flow, or MLPF, which tries to do the same thing but with neural networks. So it's natively GPU accelerated. It's open source. We have all our code available on GitHub in case you want to have a look. I also put lots of other links here to papers and talks that we have done over the years. So if you're interested to learn more about how this model works and how we used distributed training, hyperparameter optimization, and so on to improve the physics performance, you're more than welcome to have a look at these links. Now to the right here in the picture, you can see the first version of MLPF. This is from the original MLPF paper when it was introduced in 2020. So then we used the graph neural network to do particle flow reconstruction. Now more recently we have moved to using transformer models, but the concept is the same. The sort of basic loss functions we use and the inputs and the targets are in principle the same, although the model architecture has changed. So what we do is well, we're trying to improve the event reconstruction using machine learning while keeping our models portable and aimed at future possible deployment scenarios. So we're going from, as you can see in the picture here, from tracks and clusters to reconstructed particles. And the last plot there shows you the improved resolution in something called the transverse momentum of jets. All you need to know is that this is important for doing physics analysis, and it should be as low as possible. Here's a brief timeline of the MLPF effort. So as I said, we started in 2020 with a proof of concept in a Delphi simulation. This is a simplified fast simulation of a particle detector. Then we moved into what we here on the slide call a real detector, and this is a CMS simulation, where we also did first the proof of concept, and then we reached particle level state-of-the-art performance in 2022. After this, we moved back to what is called open data, and we generated a large data set based on a click-based geometry, which is another type of detector at CERN. Where we were for the first time able to prove event-level state-of-the-art performance on full simulation. After that, we did some studies on fine-tuning, where we use pre-trained models to quickly adapt to a new detector with much less training data. And most recently, we have moved back to working on CMS simulation and real data, and we are hoping to publish a paper on this with the latest results very soon. Just a note on the type of data sets that we're using. So these are highly diverse and granular data sets. We save sort of many different versions of the data set, and you can choose to work on any part that you like. So we save the raw detector hits from the detector. Then we also run traditional particle tracking algorithms and get another version of the data set where we have tracks, reconstructed tracks, and then calorimeter hits. And from this, we can either directly do ML-based particle flow, or we can first do calorimeter clustering, and then we get tracks and calorimeter clusters, and then we do ML-based particle flow. So depending on which way you go here, the problem is more or less complex. So going from tracks and calorimeter clusters is much easier than going from tracks and calorimeter hits, because well, we've done more pre-processing. So far we have only been really working on cluster-based ML particle flow, but in the future we want to also do hit-based particle flow. And the reason for this is that we remove the reliance on having some already implemented clustering algorithm to create our training data. So a note on portability. The HPC AI chip landscape is diversifying, and we need flexible and portable codes in order to make use of them in an efficient way. Our model is portable, runs on NVIDIA and AMD GPUs, as well as on Intel Habana Gaudi cards. And usually we just use a native PyTorch GDP for our distributed training. But this is not the only reason for the portability. On some types of hardware, like the Gaudi cards, for instance, only certain types of layers or operations are supported. So you need to be careful to not to use some weird PyTorch layers in your models. In our case, we use quite standard transformer blocks, which, due to the heavy use of LLMs these days, have been quite heavily optimized in most hardware. Here's just another scaling plot from the iTwinAI tool, from the InterTwin project. So here we integrated MLPF into this tool just to test it out, and here we have run it with all the different backends that iTwinAI supports. So this is the same model but running different backends to see how it scales on distributed training. Now, how does the HPO scale? So this is a test that was done as part of the CRE race project a few years ago. This was run at the Eureka DC GPU system at the JSC. Here we actually get a superlinear scaling, especially in the beginning of the plot. And this is well understood. This is due to the fact that when running scheduling algorithms like ASHA, we have to load and pause and reload models when we are training more trials than we have GPUs or compute nodes available. But after this initial phase, we sort of get something that looks more linear. So basically, we can see here that HPO lends itself really well to large-scale parallelization. So here are some results from MLPF and what we were able to achieve with hyperparameter optimization. So two different studies here, one in CMS and one in CLIC. Here we were able to decrease the validation loss by around 44% in CMS and 34% in CLIC. And this is with models that was actually already heavily optimized before we did any hyperparameter optimization, heavily hand-tuned, I should say. So we had already worked on these models for several months, trying to make them as good as we possibly could before we actually applied some more standard or automatic and a standardized way of doing hyperparameter optimization. And we were still able to get these quite significant improvements that also resulted in much better physics performance. And with that, I've come to my last slide. So we have seen that HPC systems, well, of course, they provide large numbers of powerful GPUs, and these are very suitable for AI training and for hyperparameter optimization as well. We've seen that distributed training speeds up model development cycles and model training. We've seen that HPO can significantly increase the model performance in the example of MLPF. And so in OpenLab, we have already seen that engaging with the HPC community can be incredibly beneficial. We've seen it in many different projects that we have been a part of. And at the moment, we're, as I said, working in the Spectrum project on facilitating the HPC access to the high energy physics and radio astronomy communities in Europe. And we're also submitting more applications for EuroHPC-JU research calls in the near future. And finally, I just wanted to leave you with that computing is experiencing rapid evolution of technology and techniques with large improvements in hardware accelerators and software applications. So this is a really exciting time to be working in science and computing. Thank you.